Okay, so this is you should be familiar with this look. This is the auto class page for this course. And here there's this discussion forum, which just a few of you are using. I mean, that forum over there is for you to discuss whatever you like. There's no limit to what you will discuss. The only thing is that what you discuss should be related with this course. That is the only thing I expect. You can discuss solutions of homework. You can give hints. You can even write the solutions there. I don't care. I mean, you can share solutions without me knowing it. So I don't see any point restricting you not to discuss it over here. You can put the solutions if you like. But the problem is, the only thing I want you to do is that when you write the homework that you handed in, that should be what you understand, not just copy it from auto class or from some other website. That is the only restriction. So if you just write down the solution over here, I will not do anything against that. I will not try to prevent that. But the problem is, when you write the homework, you have to convince the assistant that you didn't copy that directly. So that will be a tough job. But you can discuss the homework. You can discuss it anonymously. You can discuss it with your name explicitly seen. Just discuss it, whatever you want. And it's not just you can. In fact, I expect you to discuss, including the homework questions. Okay, any questions you want to ask before we begin? Now, I will be just reviewing what we had done on Thursday. We didn't say that in gravity. We said that in electricity. Now, in gravity, what we said that the objects move from larger potential energy to lower potential energy, which is exactly the same in electrostatics. Objects move from larger potential energy to lower potential energy, whether they are positively charged or negatively charged. But you see, for example, if your system has a potential energy of 5 joules, and then it will just move to another configuration which has a potential energy of 3 joules. This might correspond to the motion of a negative charge from minus 5 volts to minus 3 volts, for example. I mean, the numbers I'm just making up. So as a negative charge moves from minus 5 volts to minus 3 volts, the potential energy of the system changes from 5 joules to 3 joules. The potential energy always drops if you leave the system on its own. Minus 3 is larger than minus 5. So that is why we say that the negative charges move from points of smaller potential to larger potential. But whether it's negative or positively charged, they always move from larger potential energy to smaller potential energy. So this is potential energy. This is potential. Electric potential. And if you remember, the definition is that the potential energy, or let's say the change in the potential energy as one charge moves, this is equal to the change in the potential multiplied by the charge that moves. This is how we define, how we relate the changes in potential energy and the changes in potential. Yes?
So is it okay to say that no matter what side of the zero it's on, it always goes towards the zero, right? So if it's plus 5, then it goes towards 0, and if it's minus 5, then again it goes towards 0?
No, I mean, your potential energy, you can start from minus 5 volts, minus 5 joules, then it will go towards minus 8 joules. The potential energy can go from minus 5 joules to minus 8 joules. So it doesn't go towards 0. Well, you see, a physical system should always have the minimum of a potential somewhere. I mean, if you remember, the only thing we can measure is the potential difference. So you can choose your potential to be 0 at the minimum, or you might not. That's up to you. If you choose your potential energy at the minimum to be 0, then, of course, you cannot have minus 5 joules or minus 8 joules. But you can also choose your potential energy's minimum to be at minus 1,000 joules. Then your potential can drop up to down to minus 1,000 joules.
But in the universe, isn't it common for all energy will sort of dissipate and become 0, right? So this is still minus 8 joules. We know there's no negative energy, but...
No. What do you mean there's no negative energy? There is no negative kinetic energy, but potential energy can be both positive or negative.
But that's depending on how we're looking at it, right? Whether we're looking at it from the universe or from the object's perspective. Then we know it's minus or plus.
No. You see, if you look at from the universe's perspective, the universe has total energy 0. Because the kinetic energy is positive, the potential energy is negative. So there is negative energy.
So again, but wouldn't it, even if it's negative energy, wouldn't it dissipate to go to 0 instead of just...
Well, dissipation just means it goes down, not necessarily to 0. Well, you see, in our perspective, if you remember 109 course, the main thing was the forces. We started with the forces, and using the forces, we define what we call the potential energy. Well, that concept can also be generalized to electric fields or electric charges. And if you remember, the force we define has minus the gradient of the potential energy. You see, this minus tells us that the force is in the direction in which the potential energy is smaller. And this is going to the smaller potential energy is valid if you let the system, start the system at rest. I mean, if you just consider this chalk moving upwards, it is moving to a point which has a larger potential, not a smaller potential. But if you just release it, it goes to smaller potential. Well, that is mainly how we define the potential energy. We define the potential energy as such a quantity that if you leave the system on its own, it will try to minimize this thing that we define called the potential energy. It is how we define it. Other questions?
Yeah. In the midterm, we have the capacitors, and we used inside it all the time dielectrics.
Okay.
He talked about that as putting conductors. What is the main difference between putting dielectrics and conductors?
Well, you see, you can imagine a dielectric. You see, what we said for a dielectric was if you put a dielectric which are made up of insulators, the charges are not free to move, but they will slightly shift depending on the direction of the electric field. So the surface that is closer to the positive charge will be slightly negative, and the surface that is close to the positive, no, this is the positive plate, this is the negative plate. So if you put a dielectric, this surface becomes slightly negatively charged, and this surface behaves as if it is slightly positively charged. And hence the electric field inside, we said that if the magnitude we call E, E0 is the applied electric field divided by kappa. This is for a dielectric. The total electric field will be the electric field created by these charges plus these, what we call the bound charges. They are bound because they're not free to move. Now, in a conductor, what happens is the surfaces are charged, but in such a way that inside the electric field is 0. So you can imagine a conductor as a dielectric. A conductor is similar to a dielectric with kappa is infinite. So in this sense, there is not much difference. Whatever the answer is, at least in the question in the midterm, whatever the answer is for a conductor, it will also be true for a dielectric. Now, I will upload the solutions. So you can just check the solutions also. So what happens is, since the electric field is being reduced, electric field is lower now, the potential difference across these 2 points is smaller. Whether we put a dielectric or a conductor, the potential difference between the plates for a fixed charge density on the plates, the potential difference will be smaller if you put some dielectric or a conductor in between. Well, you see, it's not that why do we use a dielectric? The dielectric is always there. It is really hard to get rid of them. Air is a dielectric which fills everywhere. So we cannot get rid of them. Getting rid of them, you need to create a vacuum. Now, furthermore, when you want to use this for a practical purposes, try to make a capacitor in which the plates are separated by, let's say, less than 1 millimeter. Now, you should try it. You have the plates, you can just use some aluminum foil and try to get an area of this area and try to keep the plates separated by 1 millimeter. And let's see if you can actually do it. I mean, it will not be possible because it will bend, they will touch somewhere. The only way to prevent it, just put some insulator in between so that they will not touch, they will not conduct current if you put an insulator. But if putting an insulator just means putting a dielectric over there. So it's not really, it's not really why we put it there. It's already there. We have to put it for other reasons. And of course, it turns out to be useful also, in the sense that the capacitor, if you want to create a capacitor with a large capacitance, that is one of the problems in the homework. So you will see that the area you need, if you don't want to use a dielectric, is much, much larger than the area that you need to create a 1 farad capacitor with a dielectric. It also makes it easy to make capacitors with large capacitances.
Isn't kappa less than 1 for conductors?
No. You see, whether it's a conductor or a dielectric, inside the magnitude of the electric field is always less than the applied electric field.
But there are other electric fields between negative and positive. Do they cancel each other?
Here. Now, in these regions, of course not. But this is the electric field here. E is the electric field over here. E0 is the electric field in this region.
I mean, the potential difference is the electric fields times their separation distance. Do the two sides cancel each other?
No?
So how can we know whether its potential increases or decreases?
Well, let's see. Without the dielectric or the insulator, we know that the potential difference between these 2 plates is nothing but E0 times this whole distance. Okay? Let's call it distance 1, distance 2, distance 3. E0 times distance 1, E0 times distance 2, E0 times distance 3, we just add them up. That is the total potential difference in the absence of dielectric. This is distance 1, distance 2, distance 3. Delta V is equal to E0 times D1 plus E0 times D2 plus E0 times D3. Well, in practical applications, this D0 and D3, they are 0 anyway. But just for sketching purposes, I just leave some gap. Now, in the presence of the dielectric, delta V would be E0 times D1, because there is no dielectric over there, The electric field is not modified. Plus, now the electric field inside the dielectric is just E, and E is E0 over kappa. Times D2, and in the region D3, nothing changes. Well, this is a positive number. Kappa is larger than 1, so this number is smaller than this one. Let's call this delta V1, delta V2, which is always less than delta V2, V1, sorry. Because they look identical. It's just we replace one large number with a smaller number. So the sum is now smaller. So we are sure that the potential decreases. Whether the dielectric covers all of the volume or just part of it. And if you say kappa is infinite, still the same. The only thing we use over here is kappa should be larger than 1. And that's always true. Other questions? Because for air, kappa is very close to 1.
Why is it? Because there's matter here, there's no matter.
Well, you see, permittivity depends on various things. Like, now it's just, if you look at this picture, the charges are not free to move. They are very slightly displaced. If, due to their chemical properties, some molecules are holding their charges very tightly so that they will not be able to move, then the charges accumulated on the sides will be small. And hence, there won't be any cancellation. The cancellation here will be very small. If the cancellation is small, that means the net electric field will be almost equal to the applied electric field. That means kappa is close to 1. Or if you if you reduce the density of your dielectric, like air is not such a dense medium, then there are not many charges to displace. If there are not many charges to displace, then again the charges on the surface, the bound charges on the surface will be small. If they are small, that means kappa is close to 1.
So density and chemical properties makes air
Sure.
In the second expression, how can we be sure about the electric field between one of the plates of the capacitor and the conductor remains the same?
Well, let's see. Let's assume, do you agree with this infinite plate approximation?
Yes.
Okay, so that you agree. And let's assume that this dielectric slab is uniform. Shall we make such an approximation? Okay. So this is a parallel plate. Now here we have two parallel plates. Forget these things. These two parallel plates, the only electric field they create are in this region. So, and these parallel plates, they only create an electric field in this region. So only in this region, both of them exist and they cancel each other.
So we have to do this approximation.
Sure.
Maybe.
Sure. Other questions? About this one, about anything else? Okay, so if you remember last week on Thursday, we started discussing currents. No, that homework is still to come. You see, the problem is, if you remember, we made two derivations. Well, one of those derivations was supposed to be part of the homework, but we already did it. So we assume that we have these two parallel plates that are already charged, and we put the dielectric. And we calculated the potential energy when the dielectric is partially inserted. And by looking at the change in the potential energy, we calculate the change in the potential energy was related to the work that we had to do. And from this relation, we calculated the force that we have to exert, or the force that these plates are exerting on the dielectric. So that was one derivation. And then we had one more derivation. What we did was we just connected this capacitor to a battery so that instead of the charges, the potential was fixed. It didn't change as we insert the dielectric or not. And then we did the same derivation, and we just found out that the force was in the opposite direction. But this shouldn't be, because initially we said that we put a battery in such a way that, now we are, okay, let me first repeat, we are trying to calculate the force acting on our dielectric when it is partially inserted and with a given charge on the capacitor. That is what we are trying to do. Well, there are two things we can say. We can just charge the capacitor and just look at the change in the potential energy by very small displacement, or we can just connect the capacitor to a battery. Basically, that's how we charge it to start with, and we adjust the potential of the battery in such a way that the charge is what we have in mind. So the force has to be the same, because they're the same charge, and it's the charges that are exerting the force, not the battery itself. So we should obtain the same charge, same force, but somehow if we did the other derivation with the battery over here, we found out that the force was in the opposite direction. So there had to be something wrong in one of the derivations. The homework will be which one? But for that, we have to study a bit more the currents and study the battery. Now that will be this week's homework. Other questions? Distance? Now, the distance always affects all the properties. The distance? No. The distance, I can change the distance independent of the area. They are just completely independent properties. Now, in this week's homework, you already have one interesting question about the two capacitors. You have one capacitor, you charge it first, and then you connect it to the other capacitor, and you study whether energy is conserved or not. So are you among the ones who found energy conservation? You haven't started, okay. Well, we will discuss that problem tomorrow. Any other questions? Any questions that came to your mind in the last minute? Okay, so what we defined as the current was, well, up to now we were discussing electrostatics where charges were fixed. And we also said that if you have a conductor, for example, if you bring a positively charged object, well, the negative charges are accumulated on the side closer to the charge, and on the other side there will be positive charges left if this is a metal. And this is when the statics is reached. So eventually the charges will move to one side and they will stop. They will stop when the electric field created by these charges will be cancelled completely by the electric fields created by these induced charges. And if there is no electric field, there won't be any force acting on the charges, so they will just stop. They will stop moving to the ends. And that is why we said that in a conductor we cannot have electric field in electrostatics. But now what we are saying is, let's just imagine that, again, this is a metal. As the charges are moving, we just pick the electrons here and put them on the other side. so that we don't allow a buildup of negative charges on this side. And that is basically the device that does that. We call it a battery. Instead of this, we connect this to a battery. And what the battery does is it just picks up electrons from the negative terminal and gives electrons from the negative terminal and takes away electrons from the positive terminal. So as this battery first charges this part negatively. Well, these are in contact. Okay, these are in contact. So here we have a negative charges. Here we have positive charges. Well, I just drew it wrong. Anyway, let's stick with this picture. So if this is a conductor, the electrons will be free to move, so the electrons will keep moving under the influence of the electric field created by the battery, and so the electron will, we will not be able to pile up the electrons here, but they will just cross to the other side. And they will just keep doing this. This is what we call the current. And if you just look at this area, the current passing through that area is nothing but the total current that passes through that area in a time dt. You can just keep your time, let's say 1 second. In 1 second, you count all the charges passing through this area. That is our dq. And divide your by dt, which you chose to be 1 second, and that gives you the current running through this circuit or running through this conductor. This is how we define the current. And we also assign a direction to the current. Well, this direction is not really a direction in the sense of a vector, because this direction is mainly just choosing a plus or a negative direction. So we will say that the current running in this direction is a positive current. If the current is running in this direction, we will just call it a negative current. So we say that, okay, this is the direction of the current that is running through my circuit. It is just a convention, the choice that we are choosing the opposite direction to the flow of negative charges. Now, the concept of current is quite general in the sense that you don't have to define the current for a conductor, for a metal. For any conductor, you can define a current. For example, if you just dissolve some salt in water and connect it to a battery, in the water there will be negative particles moving in towards the positive terminal, and positive particles will be moving towards the negative terminal. Both negative and positive charges are moving in opposite directions, but the direction of the current will be always chosen as the direction in which the positively charged particles are moving, or opposite to the direction that the negative charges are moving. If both of them are moving, both definitions will be the same anyway. It's just a convention, the choice of the direction of the current. Just like, why do we call the charge of an electron negative? Just convention. And now we also define the concept of the current density. Now, if you see, this definition of the current is mainly a total thing that passes through all of this area. Now, in physics, most of the time we prefer to talk about local things. We want to talk about the property of the charge flow, let's say at this point. At this point over here, in that sense, what we do is we just choose a very small area, dA. Then through this area, there will be a very small current passing. Let's also give it a vectorial property. And there will be a very small current passing through it, dI. This dI will be equal to J, the current density. This is the definition, dot dA. So you can think of the current density as the current per unit area. Now, the total current is the total amount of charge passing through all of the area, whereas the current density is just the current per unit area. And now we also said that if the charges have a density n, and each one has a charge q, and we also define this concept of the drift velocity, Vd, then this is how we can define the current density. Now, do you have any questions about this concept of drift velocity? Now, the concept, the numerical value, I mean, the drift velocity is typically of the order of 10 to the power minus 6 millimeters per hour. It's small. It's a very small speed. But the concept of the drift velocity, the electrons will be moving randomly around. So just imagine that, okay, in 10 minutes I will say, okay, you can go for a break, and then most of you will be flowing in this direction. Some of you will be flowing back to chat with your friends. So you will be just moving randomly. The drift velocity will be mainly towards the door and much smaller than the fastest of you. So that's the same drift velocity. You are, as a group, you are drifting slowly towards the door. The same thing happens for the electrons. The electrons are moving very fast in all directions. Now, if you apply an electric field, you are basically pushing, let's say the electric field is in this direction. You are basically pushing the electrons in the opposite direction. You will be pushing the electrons in that direction, but still they will just move randomly all around. But since there is an external push in that direction, they will have a slightly larger probability that they will move a longer distance in that direction than in the other direction. And so that larger probability causes the electron group as a whole to move in the opposite direction of the electric field, and that is what we call the drift velocity. By the way, what is the size of an atom? 10 to the power minus 10 meters. What is the size meters? What is the size of the thinnest wire that you have seen? Now, 1 millimeter is huge. Let's say 0.1 millimeter of a thin wire. 10 to the power minus 1 millimeter. So still, there are like 10 to the power 9 atoms across the wire. Now, if you would just compare it with, just imagine you are the size of an atom, and this classroom itself is of the order of like 15. I can put 20 of you side by side touching each other from here to the back. Let's say 20, 30. Here we are talking about the distance of 10 to the power 9 of them. Well, 10 to the power 9, you would probably cross Turkey or cross whatever you want. So the wire, okay, you can, compared to your size, you can think that it is just one dimension, so the electrons should move in one dimension. Why does it just do this zigzag? But you see, compared to the atom, which is something much larger than the electron, by the way. So this thickness is almost infinitely thick. That's not a thin wire. That's an infinitely thick wire from the perspective of an electron. So the electron can zigzag in all directions. So it won't be a one-dimensional motion, but it will be just moving in arbitrarily in all the three directions. The drift velocity will, of course, be along the wire. So this drift velocity we are talking about, it will be along the wire. No, the eye doesn't have a direction. This one? Yes. Well, this is not really the direction of DI. This is the direction of DA, let's say. Because I doesn't have a direction. I mean, you can say that it's either, just look at this one. The direction of DI is basically, you choose a direction for the area element A, whether the current is moving in the same direction as the area element or in the opposite direction. That is this. This is a plus or a minus sign only. Well, let's see. The drift velocity is a vector. These are just numbers. So the current density is a vector.
But some things that some scalar things density being a vector sounds.
Well, you see, this is the charge density. This is the number density. This is the charge of each one. So you can think that this is the charge density. Or up to now, we were mainly showing it by rho. This is the rho. Now, of course, the charges can move in arbitrary direction. I mean, if I have a charge over here, it can move in that direction, in that direction. So the flow of these charges should be a vector. And that flow of charges is what we call the charge density. And from this charge density, we define what we call the current. Okay, the current density, we define the current. No, I didn't say that they are moving very slowly. They are moving very fast. The velocity of the electrons in a wire is of something like 10 to the power 6 meters per second. But they are moving by 10 to the power 6 meters per second in such a manner. If they move, let's say, 0.1 millimeter in that direction, they will be moving backwards by 0.1 millimeter with a speed typically of the order of 10 to the power 6, 10 to the power 7 meters per second. They are moving very fast. This is something different. This is the drift speed. So it is in a sense, you can say that this is the speed of the average position of the electron. On the average, the electron is moving in that direction, moving backwards, moving forward, moving back, moving in the other direction. So the average position doesn't change without an external electric field. But nevertheless, it is moving at speeds like 10 to the power 6 meters per second. If you apply an electric field, the average position of the electron will start to change, will start to move. And this change in the average position of the electron is what we call the drift speed, the drift velocity. This is very small.
Thermally worked out that if the drift speed is very small, why does the wire is kind of constant?
Because the electric field that you form in the wire, it forms with the speed of light. So the moment that I turn on this switch over here, an electric field is being formed in all of the wire, and that the speed at which the electric field propagates is the speed of light. So at the same instant, if you imagine this wire, the moment that you switch on the electric field or switch off the switch, all the electrons in the wire start moving at the same time with this very small speed. So that is why the light is turned on instantaneously, because at the instant that I turn on the switch, turn off the switch, close the switch, the electrons already inside the light bulb, they start moving. It's not the electrons from here reaching the light bulb. It is the electrons that are already in the light bulb. They start moving due to the presence of this electric field. And this electric field is formed instantaneously, almost instantaneously. Other questions? Now let's try to describe this motion. What is the force acting on a single electron if we exert this electric field? The force will be E times the electric field. I'm not writing the directions, so this is the magnitude of the electric field. What is the acceleration? We know the force. Let's say the mass of the electron is m. E times E over m. This is the acceleration. Now, what will be the motion of the electron? If you just leave it without any external electric field, it will move with some speed until this point. Then it will hit an atom, and then it will just move in it will move in some other direction with a large velocity speed. and then hit another atom and move with a large speed in this direction until it collides with another atom, etc. This will be the general motion. Now, if we turn on the electric field, what will happen is, as it's moving from this point to its first collision, it will be gaining some velocity due to this presence of the electric field. And that velocity will be in that direction. And from here, when it's scattered backward, until it reaches here, it will again be gaining some additional velocity in that direction. And then from here, it will scatter up to here. And from here until during this time, it will again gain some velocity, in this direction. Since it's an electron, it will be gaining some velocity in the opposite direction to the electric field. Now, if we say that the time between two collisions is tau, the average time between two collisions. So the amount of velocity that the electron gains within this time will be nothing but acceleration times tau. Well, we can identify this with the average drift. Well, this is the gain due to the electric field, but the drift velocity is nothing but the average gained velocity due to the electric field. Well, let me just put this sign. This is not exactly equal. It's not a rigorous derivation, but you would expect the drift velocity and this quantity over here to be more or less the same. I mean, the motion is a complicated motion. So there's no reason why they should be exactly equal. Other atoms, because of the vectorial nature of the velocity, etc. Well, the force is always equal to the charge multiplied by the electric field. The electron has a negative charge. So the force that an electron feels is always in the opposite direction to the applied electric field. So that's why the electrons in the conductor, if this is the direction of the applied electric field, the electrons will feel a force in that direction because the charge is negative. But if this is the drift velocity, in that case, we know what the current density should be. The current density will, if you remember the definition, the density of the electrons times the charge of the electrons times this drift velocity is E squared tau over m times E. This is the current density for a given electric field. Again, I don't expect this equation to be exact. I mean, one problem will be how do you really define this tau? I mean, you are not just looking at the electrons and following it and measuring the time between collisions. You can always define tau such that this equation is exact. But now, also, if you remember the definition of the resistivity, we had defined the current density to be the electric field divided by the resistivity. If a substance has a large resistivity, then the current density will be small. This is the definition of the resistivity. Now, if you compare these two definitions, you see that the resistivity is just m divided by ne squared tau. Now, of course, now you can ask, I mean, there were some of you asking questions like, does the resistivity or the resistance depend on pressure? They say, suppose you are compressing your metal. Now, if you exert the pressure, one thing that might change is the density. So if the volume of the metal is changing under the exerted pressure, then of course the resistivity will change. And since you are exerting a large pressure, the average distance between atoms will be smaller, since you have compressed them, so tau will change. So the resistivity, of course, depends on the pressure, but changing the volume of a solid requires huge amounts of pressure. So unless you are exerting huge amounts of pressure, the resistivity will not really depend on the pressure. For example, during the day, the pressure in this room is slightly fluctuating. There won't be any change in the resistivity, any measurable change in the resistivity. Another thing that resistivity might depend is, let's say, the temperature. Now, if you change the temperature, remember what temperature is the average motion of the particles in a material. So if you increase the temperature, what are you changing? Well, the density doesn't change. The charge doesn't change, mass doesn't change, but this tau can change. Now, there are various reasons why tau can change, because the electrons might start moving faster if you increase the temperature. If the electrons are moving faster, then the average time between two collisions will be smaller. So that is something that will change the resistivity. Or you can imagine, let's say all of the people inside are just moving randomly, and you want to cross this room. If the people are moving slowly, then you can just go straight almost. But if the people are moving faster, then there is a larger probability that some of you will hit you. So you make a collision. And so the distance you can cover, or the time between two collisions that you will make, will also depend on how fast other people are moving. In this example, if you are the electron, the average time between two collisions will also depend on how fast the atoms are moving around. So if the atoms are moving very fast, then it's more likely that you will collide with one. So higher temperature will make tau smaller, and rho will be larger. That is something you would expect. Naively, at least from this treatment. You don't expect a large dependence on the pressure, but nevertheless you do expect a dependence on the temperature. And that is how most of the electronic thermometers are actually working. So the resistivity, you can just say that it is rho 0 plus some alpha times T minus T0. So this is rho 0 is the resistivity at the temperature T0. So if you measure the resistivity of a system, of a known object, if you measure the resistivity, you know what rho 0 is at a given temperature, you know alpha of that material, then you can determine what the temperature is. And that is an electronic thermometer. Just measuring the resistance, you can determine the temperature. They lose some of the, on the average, they lose some of the energy because the atom, after the collision, starts moving faster. So if it starts moving faster, it means it has a large thermal motion and hence a large temperature. So that's why when we say the resistor dissipates the energy, that is where the energy comes from due to the collisions of the electrons with the nuclei. Other questions? Okay, see you after 10 minutes.